in a reverse situation. So could you solve this problem? Could anyone solve this problem? The original model doesn't have any intercept, but we are adding an intercept to estimate the model, because we know there are certain advantages of adding an intercept, particularly from statistical properties point of view. We have certain advantages of adding an intercept. Could you try? If not, let me just discuss about this. So this is the true model. Aditya, just one more point. As you suggested yesterday, I'm just making these materials. Actually, this component, I'm developing this material because in last year's class, we didn't emphasize much on this portion, but subsequently, based on students' feedback, their project work and all, I thought of emphasizing more on this component in this year. So I'm just fine-tuning the material. I may just take today's time, and by evening I'll upload it. So as you suggested, I'm making it little more detailed. Okay. So before we start tomorrow's lab class, these materials will be uploaded. In fact, I'll upload by this evening. For rest of the portions, materials are ready. They have been revised thoroughly. They have been updated also. But this is the portion where I'm emphasizing a bit more in this semester for your batch. Anyway, so this is the true model, and this is what we are estimating. Now, once we estimate this is the OLS estimator of lambda. But from the true model, we have this. As we take deviation from mean, arithmetic mean, we have this from the true model. As we replace this in this OLS estimator, then we are having basically this expression. As you can see, delta will come out. Then in the numerator, I will have summation of small xi square. In the denominator also, I have the same. So that part will be cancelled out. So what additional component I have? That is summation of xi into vi minus v1 divided by summation of small xi square. Now, through simplification, what I am getting? We are getting it as delta plus summation of small xi vi divided by summation of small xi square. And as you know, summation of small xi is equal to 0, so this component would be cancelled out. Now, as we take mathematical expectation of this component, we are basically getting expectation of lambda hat is equal to delta, because expectation of vi is equal to 0 by assumption. So lambda hat is an unbiased estimator of delta. That means even if we add the intercept, though the original model doesn't have the intercept, we are still getting OLS estimators that are unbiased. So as far as unbiased consistent estimator is concerned, so that from that point of view, we have no issue. There is no issue as such, because lambda hat is appearing to be an unbiased estimator of delta. Now, as regards the variance, you can see from the estimated model we are getting this as the variance, and from the true model we have this is higher than this, provided sigma square this should be W. Sigma square W is equal to sigma square. If it is higher, then again this will be, if sigma square W is higher than sigma square V, obviously from the estimated model we have the higher variance. But even if sigma square W is equal to sigma square V, still we have the higher variance of the estimated slope coefficient, because in the denominator now we have summation of small xi square. But remember, sigma square V or sigma square W, these are all theoretical values. And basically we use the OLS estimators. And we are not very sure how these two will differ. That is, sigma square hat V and sigma square hat W. How these two will be different. Because in one case, in case of V, what it would be? It would be summation of V hat I square divided by n minus 1. For sigma square hat W, we have summation of W hat I square divided by n minus 2. Because in one model, in the original model, we don't have the intercept, so number of parameters we are estimating, it is actually 1, number of coefficient. So it is n minus 1. For the estimated model, we have the intercept, so it is n minus 2. So it's an empirical question that how these two variances will differ. But if these two are equal to each other, or if from the estimated model we have higher estimated value of the variance, then obviously the estimated model will have higher variance, higher estimated variance of the slope coefficient. So that's definitely a concern, because estimated variance would increase, this will expand the confidence interval. So there may be some issues relating to testing of hypothesis and having the conclusion in the process. But if n is too large, then probably that problem will not be so significant. Anyway, one thing is sure, that adding intercept is definitely helping us in overcoming some statistical complexities what we may face if we drop the intercept, and this portion we have discussed in detail in year 1. Here just we are adding one more point. Adding intercept also helps in making the OLS estimator of the slope coefficient unbiased and consistent. Now what will happen if the situation is reversed? That is, we have the true model like this and we are estimating the model without the intercept. The original model has intercept, but we are estimating the model without the intercept. Again, the statistical properties in terms of the complexities in estimating the model that we have discussed in detail. That is, the variables are not mean corrected, we don't have the first normal equation, so we cannot necessarily say that summation of u hat I is equal to 0. And in the process, we are not in a position to decompose TSS into ESS and RSS. So all these complexities will be there. But in addition to that, what happens? As I said, the true model is this, and this is the estimated model. And delta hat, as you know, it is summation of capital Xi Yi divided by summation of capital Xi square. As we replace Yi here with lambda plus, gamma plus lambda Xi plus Ey, and as we go for mathematical simplification, by expanding this expression we are getting As you see, this lambda will come out, right? So as you can see that when we go for estimating this model by dropping the intercept, we are having lambda plus some additional component. And the mathematical expectation of this additional component is not equal to 0. And in the process, expectation of delta hat is not equal to lambda. So expectation of delta hat is not equal to lambda means with exclusion of the intercept, we are not getting an unbiased estimator of the slope coefficient. Now the OLS estimator of the slope coefficient will become biased. Again, as far as the variance, estimated variance is concerned, it's largely an empirical question. At this stage, we are not in a position to comment on this. Let us explore it empirically and we'll revisit this question. So, one point emerges from this discussion that as we drop the intercept, we have certain complexities in estimating the model. But at the same time, we now also have the problem of bias and inconsistency in the OLS estimator of the slope coefficient. And this aspect is very, very important, and we'll have further discussion on this when we revisit these issues empirically in the lab class. Is this part okay? Is this part okay? Any question on this part? Aditya?
Sir, I had a small comment. In the A part, when the true model was without any intercept.
Can you be a little louder? Hello, Aditya?
Hello, sir. Am I audible?
Yeah.
Sir, in the first part, when the true model was without an intercept, and in the estimate model, we did include an intercept. Sir, like mathematically, it's sort of, we can consider as a shift in origin. Like not even scale, it's sort of a shift in origin. So we do expect that the model estimators should be unbiased in the first part.
Right.
So, but in the second part, like it's like when the true model.
This is what, Aditya, just a small interruption. This is what we are getting, you see.
Yes.
Right. Please continue. Yeah.
Yes. So in the second part, when the true model was having an intercept, but we did not include an intercept, it I would say that it's not just of the change of origin, but it provides some statistical complications. So that's why I think our estimators are biased, I would say.
Exactly.
Mathematically, it's seen.
Exactly, you are absolutely right. I mean, this is probably the simplest way of putting this issue, as you said. And what is the statistical complexity? Now, if you see, the variables are not mean corrected. So, whenever you are estimating the model, it is not passing through the point x bar y bar. By force, you are making x bar y bar equal to 0, isn't it?
Yes, sir.
By force, you are making x bar and bar is equal to 0 by dropping the intercept. Whereas the true x bar y bar may be different. And that is exactly what it is inculcated, as you rightly pointing out. This is exactly the root of having the bias. Because true x bar y bar is something different, the set, the combination of x bar y bar, it is something different, but you are forcing them to be 0. And in the process, the variables are not mean corrected. And if you can recall, Aditya, we had another issue also in this connection, that we don't have the first normal equation, right?
Yes, sir. Because the variable is not there, we cannot differentiate.
Yeah. We don't have gamma hat, right? So we cannot differentiate summation of w hat I square, v hat I square with respect to gamma hat. And in the process, we don't have summation of u hat I equal to 0. And if we don't have that expression, we have seen subsequently that we cannot decompose TSS into ESS and RSS. So interpretation of the R square, that also becomes very problematic. You are getting R square, which is not necessarily emerging from TSS is equal to ESS plus RSS. In addition to that, we may also have certain differences in respect of estimated variance of the slope coefficient, but we don't know the distribution of sigma square V and sigma square W, how the distribution will change, and because of that, at this stage, we are not in a position to comment, but definitely we'll revisit after we carry out the empirical exercises. Is it clear?
Yes, sir. Like my question was not really a question, like it was sort of a comment / observation.
Exactly. No, what you are saying that is that the moment I am adding or dropping the intercept, I am basically shifting the origin. Is it okay?
Yes, sir. Perfectly fine.
Okay. So let us just comment on this part. Yesterday when we were discussing this, initially I didn't add because I thought you will be able to get it. So because this part will be cancelled out subsequently, so I didn't add. But as Aditya you pointed out, I have now written down it in detail, and I will upload. Once I upload, you go through the mathematical derivation. Basically, what property we are using, that is the probability limit, because we have random disturbance term or the stochastic component both in the numerator as well as in the denominator. You can see from this expression we have stochastic component both in the numerator as well as in the denominator. So we cannot take mathematical expectation of beta hat, because mathematical expectation of a ratio is not equal to the ratio of mathematical expectation of the numerator and the denominator, and that property you know. So instead of going for mathematical derivation, mathematical expectation, what we are doing here, we are basically emphasizing on the probability limit. And we are dividing both numerator and denominator by n, and in the process we are basically getting probability limit of beta hat as this, and you can very well see we have an additional component here which is making this different from beta. Thus beta hat is a biased and inconsistent estimator of beta. So this was basically with reference to committing error in measuring the independent variable. As we have seen in yesterday's class, if we commit some mistake, some error in measuring the dependent variable, we don't have any issue as such. As far as bias or inconsistency is concerned. Because if we commit any error in measuring the dependent variable, still we are getting this covariance of, say here, Vi and X, this as 0, and in the process you can see here very well this Xi star, that is the independent variable, is not endogenous. So we don't have any endogeneity problem and we don't have any problem of inconsistency. Only one problem we will have if we commit some error in measuring the dependent variable, that is the estimated variance of the slope coefficient will increase, and that we have seen, that we have discussed yesterday, that if we are committing any error in measuring the dependent variable, we don't have any problem in respect of bias and inconsistency, but definitely we have the problem in respect of efficiency. On the other hand, if we are committing mistake in measuring the independent variable, what subsequent derivation basically shows, you will see the OLS estimator will now become biased and it will also become inconsistent. So derivation part, you have a look, try to derive on your own and see if the derivation part is clear. And I have made this part detailed as Aditya you suggested, so I hope now you won't have any problem in understanding this. I'll now move to the other issue, that is choice of functional form. Here just I have highlighted a few possible functional form that often we use in economics. If you see the steps that we discussed in econometric modeling, we basically started with the underlying theory and having the mathematical model first. And then subsequently we converted this mathematical model into a statistical model. Okay, but we started with the mathematical model. And that mathematical model we expressed, we envisaged the mathematical model based on the underlying theory or the theories. Here I have basically focused on the theoretical component. I am not getting into all these in detail because these all you know. Only one thing I am highlighting here is the context. Choice of the functional form, often what we do, we use the theories, definitely, but also we rely on availability of data, and to some extent we go by our convenience also. But what I am emphasizing here is to focus the need for focusing more on the underlying theories. Often simplifying the model may help you in estimating it easily, but at the same time it it may not be providing the detailed insights. And in the process, the conclusions that you are deriving from the estimated model may not be converging with the true model. Let me just give you an example. Suppose the consumption function, the true consumption function is quadratic. And as a student of macroeconomics, you all know that in general, we define the consumption function in linear form. Then what happens? Now you see, this is the marginal propensity to consume, B, and this marginal propensity to consume in linear form, it is constant. Marginal propensity to consume is constant when I am defining the consumption function in linear form. But in practice, you know, marginal propensity to consume also depends on level of income. And often what we do, we define the consumption function when we are defining it in quadratic form. We basically define it as concave to the income axis. That means as income increases, total consumption expenditure goes up, but it increases at a decreasing rate. Now, this perspective would be very, very important. For simplification of your model, you can always assume the function to be linear. But quadratic expression may have some important implication from policy perspective. How? As income increases, you are saying that marginal propensity to consume decreases. That means people spend relatively less as the income increases. Indirectly, we can say that people save relatively more as income increases. If this is true, an important question here would be, what should be the tax structure? Right? In general, basically a progressive tax structure is suggested. That is true. But I'm here basically talking about emphasis on, say, direct tax versus indirect tax. A question here is, when tax is imposed on an essential item, it affects everybody, whether one is in the lower income group or in the upper income group. This is what normally we say. But at the same time, we know that as income increases, a particular commodity may become inferior for me and I may switch over toward a superior commodity. So, if income increases, my marginal propensity to consume may decrease relatively. It may be lower as compared to others. But at the same time, remember, total consumption expenditure is increasing and I may switch over from some commodities to some other commodities. And such changes in consumption behavior would be very, very important to design appropriate tax structure. So having a linear specification may help you in making the model simple. It may bring in convenience in estimating the model, but we may miss out many important perspectives. So for example, a critical question here would be in quadratic form, if say for example estimated C turns out to be statistically significant and negative, it essentially suggests that as income increases, marginal propensity to consume decreases. So I'll spend less. And if I spend less, I'll pay less indirect tax. So government's tax collection would be affected adversely. Does it mean that government should impose higher income tax for higher income group? So even if their marginal propensity to consume decreases, government's tax revenue is not affected because the government is now getting higher income tax because the person is earning more. And progressive tax structure, we see, of course, in our case, we have certain slabs, but essentially the structure is progressive. So I'm not getting into the details because these are all part of your course on public finance and you all have done this. Only one thing I'm bringing here is that having a linear specification may help you in avoiding statistical complexities, making the model simpler, bringing in convenience in estimation, but we may miss out some important implications in the process. And I just gave one example in terms of designing tax structure, how a quadratic specification may be useful as compared to a linear specification. Now, another example, say y is equal to a plus b by x, reciprocal. I discussed this part in econometrics 1, if you can recall. I think I had given you a question also, if I'm not wrong, that there are two alternative specifications in estimating a demand function. One is this with b being negative, another one is this with b being positive. Right? Apparently both the functions are representing an inverse relationship between price and quantity demanded. But the asymptotic properties are different. Second, if you see the slope would also be different, and hence the elasticity. And you know, we make many important conclusions in microeconomics in respect of consumers' behavior based on price elasticity of demand. And you see, for a linear function, what is going to be the price elasticity and what is the price elasticity here. So, both the functions are actually catering to the basic principle of the law of demand. That is, the inverse relationship between price and quantity demanded. But if you move beyond that, like as I said, the asymptotic properties, slope, elasticity, you will see the differences. And hence, the implications will also be different depending on which functional form you choose. And if you can recall, in econometric analysis 1, we discussed that often the choice is commodity specific. But instead of looking at that perspective, what often we do, we estimate a linear demand function like this. Another example, this semi-logarithmic function, I'll focus a bit on this, particularly when I go for application of this part in practice. I'll discuss about estimation of growth rate. And I'll show you how this semi-logarithmic specification would be important in estimating the growth rate of a function. Double log, you know, I mean, it results in elasticity. So if we are talking about constant elasticity, we basically define the double log function. One advantage is that unlike linear specification, if suppose a scatter plot is showing a quadratic function, a nonlinear function, and we are by force estimating a linear function like this, logarithmic transformation of both x and y would make this scatter plot linear, and we can have this specification. Now, linear means here I am talking about largely linear, because the scale is decreasing and in the process it looks like a linear function. Then interaction term, we discussed in last lab class the importance of having an interaction term. Often we miss it out. Someone in that class was talking about the complementarity or substitutability. Yes, it's very, very important. But there are some other perspectives also, like how the impact of x on y is changing with changing z. Means impact of x on y is no longer constant, rather it changes with changing z. So is elasticity. One simple example, impact of increase in price would depend on income level also, and that is the fact. If price increases, the lower income group people would be affected more as compared to the high income group people. But what we do often, instead of recognizing this interaction term, we write it in linear form like y is equal to a plus bx plus cz like this, and in the process we make the impact constant. And we miss out many, many important perspectives. As I said, impact of a change in price would also depend on income level of the consumer. Simple example, if price goes up, the impact would be more, the adverse impact would be more on the lower income group households as compared to those in the higher income. Then logistic function, you know, again mathematically you know.
Hello sir. Hello sir.
Yes.
Sir, in the interaction term, it is it purposeful that we are not taking the, in this case, independent term for z standalone? Like it's depending on the situation. Like for example, plus dz in the model.
Can you repeat the question?
Sir, in the functional form of interaction, y equals to a plus bx plus cxz, we have considered like the interaction of x with respect to z, but we did not, in this specific functional form, we did not consider the independent effect of z. So is it like
that you can add? No, there is no purpose. Just I have just to compare across the functions. No, because see, I have here considered only one independent variable throughout. Just to compare across alternative specifications, I have taken only x. You can always add, say, dz.
Yeah, that's what. Yes, that's what I was asking.
No. There is no purpose. Just to have consistency, I didn't add dz. You can always add dz. No issue.
Yes, I thought it was more of a situational. So maybe in this case you have omitted dz.
Actually, even if you add z, this doesn't alter the effect of x on the effect of x on y. Isn't
no,
it?
But it would have some effect of like the effect of z on y would not be captured if we didn't add that.
Right, you are absolutely right. As far as effect of z on y is concerned, we must have that component, that linear component, as you are saying. But here basically I am trying to understand with respect to x. If you see all the specifications that I have pointed out, all are basically just to have a consistency throughout. I didn't add z, but you can always add the z component. No issue. There is no purpose as such. Okay.
Yes, I got it.
Sir, a doubt. So rather than taking the interaction, if we just simply control for z, would we still be able to answer the policy question, that controlling for income?
Yeah, very good question. That not different income groups.
Sir, I was not able to
add some dummy variable. Dummy variable is also essentially it is resulting in some truncated functions, isn't it?
Sir, can you please repeat? I was not able to hear you.
What I'm saying, suppose there are 3 income groups. Hello? Hello, Shashank, am I audible?
Yes, sir, now you're audible. Your voice was breaking earlier. Now it's
okay. Yeah. So what I'm basically saying, you can drop income from here and you can estimate separate demand function for different income groups. Are you getting?
Yes, sir.
Or else, what you can do, you can control that by adding a dummy variable or dummy variables for different income group. The way we did, no, in truncation model.
Basically, if you have 3 income groups, you make a vector. Maybe like if the belongs to third.
Basically, so what I do,
0.
Depending on income level, I'll divide the entire set of observations into 3 income groups. And I will estimate separate demand function with respect to price for each of these income groups. And I will compare. This is one possibility. Second possibility is that I will estimate a combined model, right? But I will basically control for the groups by adding different dummy variables. The way we did before carrying out chow test. Is it clear, Shashank?
Yes, it is clear.
We will do this part in tomorrow's class, in tomorrow's lab class. But it's a very, very important question. That if I want to understand the impact of income on demand, I can still get some insights without adding income into the model. But in that case, what I need to do, basically, I need to go for separate regression for each of the income groups. And then I can go for comparing the coefficients. Which one is larger or which one is lower. But bringing in interaction term, basically what you are saying, Shashank, and what Aditya was telling, just it is nothing but this. Now, Aditya, if you see, this is nothing but a dummy variable specification. Let us assume that Z is the dummy variable. And dummy variable, it is equal to 1 for higher income group, it is equal to 0 for lower income group. Then this specification is nothing but what? Y is equal to A plus BX plus C. What? DX.
Sir, it would be again the analysis of the slope and intercept in different groups with respect to dummy variables.
Exactly. So here Z you can treat as a dummy variable, isn't it? Z you can put it as a dummy variable with Z taking value 1 for higher income group and taking value 0 for lower income group. Am I right, Aditya?
Yes, sir. Same as we did previously also.
Yeah, this is what we did previously. Now suppose you have multiple income groups. Then it can be Z1, Z2, Z3 like that, depending on how many income groups you are having. Is it okay? Is it okay?
Yes, sir. Like we already have experience.
So just let me quickly complete the last one, that is the logistic function. Again, logistic function, I'll discuss on this in detail when we go for estimating logic model. Logistic function, estimation of logistic function is quite common in economics. Say for example, let us assume that Y is the probability of buying a new house. Let us assume that Y is the probability of buying a new house and X is income. Now this CDF will definitely follow a logistic form. It's in the sense, at a very low income level, even if income increases, there will be very infinitely small increase in probability that I'll buy a new house. Because at a very low level of income, even if the income increases, the probability of buying a new house is unlikely to increase. Similarly, at a very high income group, even if income increases, it is very unlikely that I will buy a new house because I have already a house or a few houses. So the CDF in this case will be enlarged S set. And that is how in some such cases we basically go for estimating the function which is in logistic form. And here I just added the derivation for your convenience, and you know I don't want to repeat that. Just I'll quickly go through. So this is the function, and what we are doing, we are taking 1 minus y, and then this is what we are having. So 1 y by 1 minus y, this is the form, and then taking log from both the sides, we are having this as the slope and this as the elasticity. And this part I'll add a little in logical substance, means with some example, and I'll upload. Then just two more quick points. One is the restricted, this is basically a statistical test for linearity. So Shashank, you talked about Ramsey test for linearity. We can also carry out restricted F test. Okay, so this is the restricted model, the linear model is the restricted model, and cubic form is the unrestricted model, and the null hypothesis is theta 2 is equal to theta 3 is equal to 0. Okay, and so this is how we can compute the F stat and we carry out the test. Rejection of the null hypothesis suggests that the function is not linear. So if the null hypothesis is rejected, it basically suggests that at least one of theta 2 and theta 3, at least one of them is 0. Hence the function is not linear. And then Lagrange multiplier test for inclusion of variable. Suppose this is the restricted model and this is the unrestricted model. Means I need to test whether I can add some additional variables like xm plus 1, xm plus 2, xk. I have estimated a model with m number of independent variables. I just would like to test if I can add some additional variables like this. So the null hypothesis, as usual, the slope coefficient of the additional variables, they are equal to 0 simultaneously. What basically I need to do, first I need to estimate the restricted model. And I need to get the residuals. Now if these additional variables or some of the additional variables belong to this model, then there will be a significant relationship between these variables and the residual. The residual will now have, because the part that was excluded in the original model, they belong to this residual. So the residual, a strong association with these variables. So what I need to do basically, first I need to estimate the restricted model. I need to get the residual and then regress the residual on the remaining independent variables. And in the process, you will get the R square. For large n, as you know, n into R square, it asymptotically follows chi-square distribution with degrees of freedom k minus n, means the number of additional regressions. And rejection of the null hypothesis indicates that the additional variables should be added into the model. So here one, we had carried out a restricted F test, and in EA2, and one more test in addition to Ramsey test, of course. Ramsey test, we say that basically whether we have any omitted variable bias. Remember, quadratic form or cubic form, they also result in omission of some components. It's not exactly variables, but some components. So this is another test that we need to focus on, we need to understand. And in tomorrow's class, we'll be carrying out this, both in Stata as well as in Excel. And Aryan, you are there, you have fantastically summarized what we discussed in lab 1, I mean the very first class.
Yes, sir.
In session 1. So I have kept that for tomorrow's class. I would basically suggest you to just make a brief presentation of 5 minutes or so in tomorrow's class. To begin with, the summary by you, and then we'll proceed. So I will stop here. Sorry, I couldn't take if you have any additional questions, but the group is the same. Those who are here in the theory, you all are there in the lab as well, so we can just carry out the discussions in the lab class if we have any further questions. But again, please participate in the discussion. Let us have more discussions in the class. What In the process, we may slow down a bit, that is true. But at the same time, we shouldn't miss out the discussions. And one more advantage is that in this course, as I said, the group for theory and the group for lab, it is the same. And hence, even if we miss out something in the theory course, we can continue the discussion in the lab and vice versa. Unlike the problem what we used to have in year one, because some students were having theory, others were not having lab or theory. So that sort of problem was there in year one, but that problem is not there in year two. So we can in fact combine the two courses and have continuous discussions. Some component of lab subsequently I can bring in here also. Similarly, some component of theory we can discuss there also. Is it okay? Hello?
Yes, sir.
Okay, just one more thing. I mean, tell me, I could see some attendance issue in morning class on Monday. You can think of, I mean, again, it's not from my side, it is entirely from your side. If you are free, one class we can think of, or if you need, rather I'll put it in this way, if you need, one class we can think of shifting from 8 o'clock to some other hours. One class. We don't require any adjustments because the set of students, it is common. I mean, it is basically from economics. Just one class, that is 8 o'clock class. If you think of, or else if you are comfortable with, we can continue as it is. Nice. Just think of and let me know. Because I want, I mean, I always like to have all of you attending the classes. So should we stop now?
Yes, sir.
Okay,
Yes, sir.
okay, thank you so much. Thank you so much. Aditya, I'll upload sometime by tonight. Okay?
Sir, please upload the MLE also. I could not find that.
Emily, yeah, Emily, both. I'm writing it in detail. As you suggested, I'm writing down in detail.
Okay, thank you, sir.
Okay, okay. Only for this portion, I need to just fine tune the material. As I said, for other components, we don't have any issue. Already the materials are developed, revised, and so we can straight away go for uploading those materials. Okay, for other components. Only for this model selection, I'm just developing it. So maybe I'll be just delayed a bit, but for this component, I'll add by tonight. Okay, thank you so much. Let us meet tomorrow in the lab class.